So this question is about using state feedback control with an observer, and we're given a dynamical system to consider written in a state space format, x dot equals ax plus bu, y equals cx plus du, and the first thing we're asked to do is to draw a signal flow graph that realizes this equation. And if we did that, we could also implement it directly in Simulink. Then what we do is we're going to analyze the circuit, the system, and substitute in when we use full state feedback control. Then it's basically wants us to look at writing down the equation that we get to estimate the state using a Leuenberger observer. And finally, draw the signal flow graph for a state feedback controller, which is using an estimate of the state from a Leuenberger observer. So let's start off by looking at the equations and writing down what the signal flow graph would look like. Here's the complete version. If you're drawing this from first principles, well, what I would recommend you do, obviously give yourself enough space, but write down x dot and x down first. So x dot needs to pass through the integrator block in order to get x. So that's this bit at the bottom here. And then we just basically have to go through the equations and make sure all the paths actually give you the result the equation's demanding. So we want x dot equals ax plus bu. So you look at x dot here, and that's got to be the sum of ax and the sum and bu. So x here multiplied by a gives us ax here, and we want a term from the input coming in. So the input comes in from the left multiplied by b. So we've got bu coming in there. We add them together and we get ax plus bu, and that is going to be our x dot. That goes through the integrator, we get our x, that's fine. Now we just have to put the output equation in, the y here. So the y is going to be made up of cx. So we've got the x here coming through, the c, it gets sailed by c, so we have cx here, and we put that into a summer, and we've also got to add on the other term, which is u coming through here, times d, so du coming down here, and that gives us our yt. So now what we're going to do is we're going to look at the state space equations, and we're just going to say we're going to use full state feedback, which means that u, the input, is now going to be given by minus kx. So we just have to substitute u equals minus kx into these two equations here. That's nice and easy to do. So first one becomes x dot equals ax minus bkx, and we can factorize out the x. Second one is y equals cx minus dkx, so we factorize out the x again, and we have the new equations of what the system now looks like if we have state feedback control. So we've got our equations, and now we can draw this this modified system onto our signal flow graph. In fact, all we really actually have to do is say, look, all we're doing now is, rather than having u just going in as it did before, we now know u is now equal to minus kx. So we tap off the x, we multiply it by minus k. Don't forget these things are vectors, and then we pass that to the input u. And in this particular case, I've also got a summer, so I can actually also add on a reference value if I want to do that. Okay, so now it's asking us to look into what a direct basically what the observer does in terms of how it all works. Let's go through an observer from sort of kind of first principles a bit here. If we had a direct state feedback controller, what we'd be doing is we'd have a goal that we want the system to actually achieve, and if you just look at the feed forward path to start with, you might scale it, you might put it through some kind of function, but basically it goes straight into the plant, maybe modified a bit, and generates an output. And if we had full state feedback control, we'd get the full state from the plant, we'd multiply it by k, and then we'd take it away from the input, right? And this is giving us, in other words, this would be our full state feedback coming through here. In this case, the goal would have to be one for each of the states. But what we can also do, and there's various reasons for doing that, is actually have a model of the plant, right? So we could actually not directly use an estimate of or a measurement of the state from the plant. It might be that we can't do that, but what we can do is have a model, a simulation of the plant that we can predict the state from. And we could then run a feedback controller using the predicted version of the state like this. So we in order to do that, the command going into the plant has got to be split and also going into our forward model. Unless this goes back through the gain and back up to the beginning to take away from what the goal is. Now, obviously, this is a feed-forward controller, right? We're not actually doing anything. We're not looking at the output at all from what's happening here and affecting anything that's happening down here. So that's got its issues. So in actual fact, what we like to do, if this model of the plant differs a lot from the plant, then this isn't going to work very well. So we want to do is we actually care about what the actual output's doing. Can we then come up with some sort of correction term so we can get the thing to work better? And the idea is, yes, we can, and we're going to define what's called a prediction error. So we look at what the plant's doing, and we predict what we think the plant's doing using our forward model. It could just be the outputs that we've got available. And we compare what we think the plant's doing with the model with what the plant's actually doing. We take away from the actual output what we predict the output to be, and we end up with this prediction error. So if we can use this prediction error, then the nicest thing would be so if we could then feed this prediction error back to the plant such that in a feedback loop, the idea would be then we can modify what the plant does so the prediction error goes away, right? So it goes to 0. And when that happens, what the plant prediction the plant model predictions doing will be the same as what the plant's actually doing. So we can actually get a better prediction of the states of the system. That's the basic idea. So in a Lüneburger observer, what we do is we calculate the forward model, we calculate the full state and use that for feedback. But then what we do is we look at the output, compare it with the actual output of the system, and scale it by L, which is the Lüneburger gain, and then put this into the prediction of our actual forward model in order to drive the prediction error down. So we've got this feedback controller trying to get rid of the prediction error. And if we do that, we can get a better estimate of state. So if we do that, it doesn't even matter if the forward model isn't a very good model of the plant. It still may well be able to do a reasonably good job at making a prediction because we're actually using the real output in order to change the actual prediction. Right? So that thing there is using a feedback controller scaled by the Lüneburger gain in order to get a better quality prediction. We won't worry about delays at this time, but basically there are issues with delays that you have to deal with. Look at the lecture notes if you want to know about that. This is not being asked in the question. So, previously from a feed, well, from an open loop system, we've had the equation that the state x dot equals ax plus bu, but we have a slightly different formula for the predictor that we have now from the Lüneburger, because what we have now is we have an estimate of the state. We're not saying it's the actual state. The actual state is x. We're going to call the predicted state x hat. So we have an updated equation now that x hat dot equals a x hat plus bu. That's basically the feed forward part of the model that we've got, but we've also got this prediction error term. We also add on the scaled version of the prediction error, and the scaled version of the prediction error is L multiplied by output of the real system, take away our predicted output. So that's basically the prediction correction term that we actually have to add on to this, and we have to find L in order to get that to work, right? And in order to do so, we will generally look at the eigenvalues of A minus LC and put them where we want them to be by choosing L appropriately. Okay. So if we actually now draw the whole system, here we've got our state space model of what the plant is like. In fact, this is all written down as a state space model. This could be in actual fact just a black box, and you've got the input and you've got the output. We're just doing it like this to make it a bit more easy to follow. When we put full state feedback control in, normally what we do is we tap, if we did it directly from the system, we get it from here, from X, and we'd feed that through -K and we'd feed that back. But now we're using this Lüneburger observer, so we've stuck down here the observer, which is effectively a model of what we've got up here, right? So that this is the model, this is the plant in this case. This is a model of the plant, so it's got an X hat dot and an X hat rather than X dot and X. So X hat means it's a prediction. So now what we do is we calculate this predicted state X hat, and we use the predicted state in the state feedback. So X hat gets multiplied by -K, and that gets fed back to the beginning. And if we want, we can put the reference term in. So this bit down here now corresponds to adding on this Lüneburger predictor, and we're using full state feedback control from the estimated version of the state of the system.